Okay, today we're looking at Kimi Linear, an expressive, efficient attention architecture. If you're grappling with scaling LLMs to, well, truly massive context windows, like 1 million tokens, this paper might just have the breakthrough you need.
Absolutely. The core claim here is pretty bold, actually. Kimi Linear proposes this hybrid linear attention architecture, and they argue quite rigorously that it actually outperforms standard full attention, what they call MLA or multi-head latent attention, while being massively more efficient.
Right, that double win better quality and way faster is what really catches the eye. And the key piece of tech driving this is Kimi Delta Attention, or KDA. It's based on Gated DeltaNet, but adds this fine-grained control mechanism for the model's memory.
Yeah, and for anyone actually deploying these models, the efficiency numbers are critical. They're talking up to 75% less key value cache usage. And think about decoding at 1 million tokens. Kimi Linear apparently gets up to 6 times the throughput, measured in time per output token, TPOT.
And they seem to have tested this thoroughly. Short context, long context stuff like the ruler benchmark, even reinforcement learning scaling, all trained using the same 1.4 trillion token recipe.
So yeah, they're positioning Kimi Linear as potentially a drop-in replacement for standard attention, not just some niche optimization.
So maybe we should start with the problem itself. Why do we even need something like Kimi Linear? Because understanding the bottleneck is key.
Good point. The field is pushing towards agentic intelligence, models that need to handle really long sequences of interaction.
Exactly. Think about complex tool use, or planning over many steps, or just remembering a really long conversation history. You quickly get into context way beyond 100K tokens, maybe even up to 1 million or more.
And that's where standard softmax attention just breaks down, right? Computationally.
Totally. It's that quadratic time complexity, O of t squared. Compute costs explode. But honestly, even if you had infinite compute, the memory is often the real killer. The KV cache grows linearly with the sequence length. Right. So even if the map takes a few seconds, you just run out of GPU memory trying to store the state for all those tokens. Kills throughput, kills interactivity.
Precisely. It makes real-time interaction at these huge context lengths practically impossible, or at least prohibitively expensive.
Okay, so we've seen attempts at linear attention before, things like Gated DeltaNet, GDN, which you mentioned KDA builds on. Why didn't they solve this? They have linear complexity, O of t.
Well, historically, pure linear attention models just haven't performed as well. They tend to struggle with capturing complex dependencies over long distances or doing precise in-context retrieval compared to full attention.
Why is that? Is it like they forget things too quickly?
Sort of. They have a finite internal state, like a recurrent neural network, and that finite state has limitations in its capacity and, critically, its ability to precisely track positional information over very long sequences. Their expressivity has been the main drawback.
So the challenge is, how do you get that OT efficiency without sacrificing the quality and the expressiveness we get from quadratic attention?
And that's exactly where Kimi Delta Attention, KDA, comes in. It builds on GDN, like we said. GDN viewed memory updates, kind of like online gradient descent trying to reconstruct something, stabilized by a simple scalar forget gate. Think of it as a basic weight decay on the memory.
Okay, a single scalar gate, alpha, for potentially hundreds of thousands of tokens across multiple heads. That sounds really coarse, like one thermostat for a giant building.
That's a great analogy. It is too coarse. And that's the key refinement KDA introduces. Instead of one scalar gate per head, KDA uses a channel-wise gate. Mathematically, it's a diagonal matrix, diag alpha.
Whoa, okay. So moving from a single number to a whole diagonal matrix for the gate, why does that specific change unlock so much expressivity?
It allows for much, much finer control. Now, each individual channel within that recurrent state can have its own learned decay rate. Some information channels might need to persist for a long time, others can fade quickly.
Got it. So instead of the whole head forgetting uniformly, you get this nuanced per-channel memory management. Does that also help with knowing where information came from? Positional awareness?
Absolutely. That fine-grained control significantly enhances both the memory decay dynamics and the positional awareness. The model gets better at distinguishing recent information from very old information just based on how different channels decay.
This sounds like it's blurring the lines between the attention mechanism itself and positional encoding.
You're spot on. This channel-wise gating essentially makes KDA function as a form of multiplicative positional encoding. The way the recurrent state transitions over time becomes data-dependent and learnable.
Which is different from something like ROP, rotary position embedding, which has fixed rules.
Exactly. ROPE relies on specific mathematical properties, like orthogonality. KDA relaxes that. The positional information is learned implicitly through these dynamic, data-dependent state transitions. This might even lead to better extrapolation on sequences longer than seen in training, which is a known challenge for fixed encodings like ROPE.
Okay, so KDA provides the expressivity. But linear attention still needs to be fast on actual hardware to be useful. You mentioned deployment pain points earlier. How does Kimi Linear address the raw speed aspect?
Right. This leads into the hardware efficiency part, specifically how they leverage the diagonal plus low rank or DPLR structure.
Ah, DPLR. Powerful for modeling sequences, but often really slow and hard to parallelize efficiently on GPUs, right?
Traditionally, yes. The general DPLR formulation involves several matrix operations that don't map nicely to GPU kernels. But Kimi Linear uses a clever, specialized variant of DPLR.
How is it specialized? What did they change?
They introduced a structural constraint. They essentially tied some of the internal variables in the DPLR math, specifically binding A and B to the key vector K. This simplifies the underlying computations quite a bit.
Okay, sounds technical, but what's the practical upshot of binding those variables? Does it avoid certain problems?
It does. One major benefit is it helps avoid numerical precision issues that can plague other fast linear attention methods, like GLA, global linear attention. Those issues often force developers to add extra steps, like secondary chunking, which adds complexity and can slow things down again. KDA avoids that.
So stable numerics even at half precision. And does simplifying the DPLR math translate directly to speed?
Yes, significantly. By imposing that constraint, they cut down the number of required matrix computations within their chunking algorithm from 4 to just 2. They eliminate 3 whole matrix multiplications per chunk.
Wow. Fewer matrix multiplies is always good news for speed. What kind of speed up are we talking about at the kernel level?
Compared to the general DPLR approach, this specialized KDA version yields roughly a 100% improvement in operator efficiency. That's nearly a 2x kernel speedup for sequence lengths up to around 64K, which is huge. It makes the linear attention part genuinely fast.
Okay, so we have an expressive and fast linear attention module with KDA. But the final Kimi linear architecture isn't purely KDA, is it? They use a hybrid approach.
That's right. They don't fully replace standard attention. Instead, Kimi Linear interleaves KDA layers with standard full attention layers, the MLA layers we mentioned earlier.
And they landed on a specific ratio.
Yeah, empirically, they found a 3-to-1 ratio worked best for the trade-off between quality and throughput. So for every block of 4 attention layers, 3 are KDA layers, and 1 is a full MLA layer.
Interesting. So even with KDA being so expressive, they still keep that one full attention layer. Why? What does it add?
That MLA layer seems to act as a sort of global information consolidator. It ensures that any very long-range dependencies or perhaps subtleties that might not be perfectly captured by KDA's finite recurrent state still get processed by the full quadratic attention mechanism. It's a belt and suspenders approach for quality.
But it still gives massive efficiency wins overall, right?
Yeah.
What does 3 out of 4 linear layers mean for memory?
It means you reduce the active memory footprint and, crucially, the KV cache usage by up to 75% during inference, especially for long sequences. And that's transformative for deployment.
Right. 75% less KD cache means you can potentially run batches 4 times larger on the same GPU or use cheaper hardware. That directly translates to lower cost per token and higher throughput.
Exactly. It fundamentally changes the economics of running models with large contexts.
Now, probably the most surprising design choice for me was the positional encoding strategy. They use no position encoding, no PE on those full MLA layers.
Yeah.
Why remove positional info from the one layer that sees everything globally?
It seems counterintuitive at first, but it's a very deliberate choice tied to the KDA design. By using no PE on the MLA layers, they are essentially forcing the KDA layers to handle all the positional information and recency bias.
Ah, so they're fully committing to KDA as the position-aware component, leveraging that implicit positional encoding we talked about earlier.
Precisely. The MLA layer's job is just reduced to mixing information globally based on content without needing explicit position inputs.
Okay, but what's the practical engineering benefit of doing that? Why not just put ROPE on the MLA layers too?
2 big reasons. First, using no PE allows those MLA layers to be converted during inference into pure multi-query attention, MQA, which is extremely efficient hardware-wise. MQA shares keys and values across heads, saving memory and compute.
Okay, so it unlocks further inference optimization. What's the second reason?
It massively simplifies training and fine-tuning for long contexts. You don't have the headache of adjusting row P parameters or dealing with extrapolation issues when you want to increase the context length from, say, 32K to 128K or beyond. KDA handles the length of generalization implicitly.
And did their experiments back this up? Did the no PE version perform well?
Yes, their ablation studies were pretty clear. The standard Kimi Linear with no PE on MLA layers excelled on long context benchmarks. A version where they did add row P to the MLA layers only achieved similar scores on short context tasks and didn't show the same long context strength. It really reinforces that KDA is effectively managing the positional aspect.
Okay, the theory sounds solid, the architecture clever. Let's get to the results. How did Kimi Linear actually perform in practice, especially on those crazy long sequences?
Well, first, just looking at training efficiency itself, how much model quality you get per unit of compute, they found Kimi Linear was about 1.16 times more compute efficient than the MLA baseline during large-scale pre-training. So cheaper to train for the same performance level.
1.16x is nice, but the inference speedup is probably the main draw for most people. What were those numbers again?
Yeah, the decoding speedup is where it really shines. At a 1 million token context length, Kimi Linear achieved a time per output token, or TPOT, that was 6.3 times faster than the standard MLA baseline.
6.3x faster. What are the actual times?
For Kimi Linear, it was about 1.84 milliseconds per token. For the MLA baseline, it was 11.48 milliseconds. That's a massive difference. It takes you from maybe usable offline to potentially interactive speeds, even at that scale.
That's incredible. What about the initial processing, the prefill stage? That can also be a bottleneck for long prompts.
Also much better. For 1 million token sequences, the prefill time for Kimi Linear was 2.9 times faster than MLA. Again, this is largely enabled by the reduced memory, allowing much larger batch sizes to be processed in parallel.
Okay, speed is great, efficiency is great. The million-dollar question, did they sacrifice quality to get there? How did it do on actual benchmarks?
Remarkably, no apparent trade-off. In their comparisons, using the exact same 1.4 trillion token training data, Kimi Linear consistently outperformed the MLA baseline and also a hybrid baseline using the older GDN approach.
Outperformed even on standard short context stuff.
Yes. For example, on MMLU Pro, which tests multitask understanding at a 4K context, Kimi Linear scored 51.0 compared to 47.2 for MLA. It also showed leads in general knowledge tasks, reasoning benchmarks like math and code generation, and even Chinese language evaluations like CEVAL and CMMMLU.
Wow. Okay, so better on short context. What about its specialty long context?
That's where it really pulled ahead. On a suite of long context benchmarks evaluated at 128K context length, Kimi Linear achieved the highest overall average score.
Any specific benchmarks where it stood out?
Yeah, it showed a particularly strong lead on Ruler, which heavily tests long-range retrieval scoring 84.3 versus MLA's 81.3. Also, strong performance on things like repo QA, which involves finding information in code repositories.
And you mentioned reinforcement learning earlier. How did it fare in more complex adaptive training scenarios?
Also very well. They trained models using RL specifically for mathematical reasoning tasks, which requires handling long chains of thought. Kimi Linear demonstrated superior convergence, it learned faster, and reached better final performance on tough math test sets like Mat 500, and even problems from the AIM competition, compared to the MLA model trained with the same RL process.
So across the board, pre-training efficiency, inference speed, short context quality, long context robustness, and even complex RL training, Kimi Linear seems to come out on top.
That's certainly the picture painted by the paper's results. It looks like they've genuinely managed to break that historical trade-off between the efficiency of linear attention and the quality of full attention.
And the key ingredients seem to be that fine-grained channel-wise gating in KDA, combined with the specialized hardware-efficient DPLR implementation.
Exactly. And then wrapping that in the Smart 3.1 hybrid architecture, with the no PE strategy for the MLA layers, it all comes together to give you that quality boost alongside the 75% memory reduction and the massive up to 6x decoding speedup.
And critically for the community, they've released the code, right?
Yes, that's huge. The KDA kernels, integration with popular inference libraries like VLLM, and even pre-trained and instruction-tuned model checkpoints are open sourced. So you can actually try this out, benchmark it on your own tasks, and build on it.
It makes it much easier for people to verify these claims and start using it.
Definitely. Which brings us maybe to a final thought for you, the listener, to chew on. We've seen how KDA effectively acts as this learned, dynamic, positional encoding system baked right into the linear attention layers.
Right, potentially replacing the need for explicit encodings like ROPE.
So the question is, if the expressiveness and the positional awareness we used to rely on explicit methods for can now be fully captured, maybe even surpassed, by these dynamically gated recurrent states within efficient linear layers, does this Kimi Linear paper signal the beginning of the end for traditional explicit positional encodings in the next generation of highly optimized LLMs? Is the future implicitly learned positionality?